Hi, my name is Rachel Wities, and we're going to talk about sending BERT to med school using structured knowledge. A little bit about myself. I work as an NLP data scientist at Zebra Medical. I hold a master's degree in computer science from BIU NLP Lab. And for the past few years, I'm learning to understand how doctors think and teach algorithms to understand doctors. I'll start with a story. A year ago, I took a head CT scan, and a few days later, I got to my mail the radiology report interpreting the findings on my scan. So I don't have any medical degree or training, but I did review for the past few years a lot of these kinds of medical records as part of my work in Zebra Medical. And at this point, I like to call a game. I call how long before calling a real doctor. How much of the report I can actually understand before I need to call a real medical doctor and ask him questions. So the beginning was easy, unremarkable. I've seen this word a lot. It's a good word. You want to have it on your report. Normal in size is also great. No evidence of is fantastic. A good word to have on your report. But then I got to this sentence and I got stuck because I never seen the term retention cyst before. So this is where I lost, and I had to call a doctor who told me that this is actually a good type of rare. This word is so unimportant that many radiologists never mention it in their reports, and this is why I'm not familiar with it. So what we're going to talk about today is how BERT would do on this test, because surprisingly, he would have a lot of similar problems to mine. So this is what we're going to talk about. We're going to see why medical records are hard for BERT. I'm going to explain a little bit about medical ontologies. And then we're going to do some BERTology. We're going to open BERT up and inject knowledge into it using the ontologies. So let's start with why medical records are hard. BERT is a very popular model in NLP, which, like many state-of-the-art models in NLP, heavily relies on a pre-trained language model, which is pre-trained on a lot of unlabeled documents, and then fine-tuned on a small amount of labeled data. So this approach is very fruitful and works very well for many reasons and is very popular. But it does state a problem for small specific domains like the healthcare domain, because the pre-trained language model that was pre-trained on a lot of general text doesn't represent the language model of medical text. But this is actually a problem that was fixed a few months after BERT was published. There was published BioBERT, which was pre-trained on a large amount of medical records and performed better on medical tasks. And then clinical BERT and then BlueBERT, all pre-trained on clinical records and having better and better performance in medical tasks. But is this enough? Is giving BERT more and more unlabeled medical data to see is going to make him understand medicine? So not exactly. He would still have the same problems that I have in my game. First of all, underlying medical knowledge. Doctors have a lot of knowledge that they don't explicitly state in the report. So BERT would actually never see some of the things that led them to write what they write. Another problem is what I like to call the all happy families effect. Based on the first sentence in Anna Karenina, happy families are all alike. Every unhappy family is unhappy in its own way. So we actually see the same phenomenon in medical records. The happy sentences, the sentences that say there is no this and that is normal, appear frequently, and BERT will see them a lot during the pre-training. But the unhappy sentences, which are actually what is interesting to us, the sentences that actually contain a specific finding, are all different and not so frequent, And BERT would not see a lot of them, or at least won't see them as frequently as the normal sentences. So this is another problem we have. And the third problem is that, well, we could say, okay, we can't have this knowledge in pre-training, but we can inject it during the fine-tuning phase using labeled data. But unfortunately, the healthcare NLP also suffers from lack of labeled data because of the need of confidentiality, because labeling medical records requires a high level of expertise, and because the medical language is actually contains a lot of different sub-languages. So we see that no matter how much unlabeled medical records BERT is, he still has these three problems to deal with. But in the medical domain, we do have one strong advantage. We have medical ontologies. What are medical ontologies? Are a few examples. Medical ontologies are basically manually crafted knowledge graphs containing hierarchically based medical terms. Here we can see two very popular ontologies, the mesh ontology, which was created in the 1960s, and UMLS, which is a little more new. It was created in 1987. All of them containing thousands and hundreds of thousands medical concepts. The basic properties that each ontology would have is a controlled vocabulary of medical concept, manually gathered by doctors, hierarchical structure of is A, pneumonia is a type of disease, streptococcal pneumonia is a type of pneumonia, and synonyms, different ways to state the same finding. Lung infection, pneumatitis is all the same as pneumonia. Why doctors love ontologies and why they created them in the first place? First of all, term standardization is very important in medicine. One of the main ways of doctor to let other doctors of the same patient understand what they saw is through the medical records. So it's important that the terms would be standardized and the other doctors understand what they meant. Another thing is that in ontologies, the importance and severity of findings is better represented than in free text. I spoke before about the all happy family phenomenon. We don't have it in ontologies. In ontology, each finding would be represented in respect to how important or severe it is. And the other thing, the last point, is healthcare digitalization. Originally, the ontologies were created in order to support digitalization of medical records. And the thought was that it will be easier for computers to understand this kind of structure than free text. But ironically, the state-of-the-art NLP models are actually dealing better and are trained to deal with free text and not with ontologies. So it requires a little bit of changes in their architecture to support injecting knowledge from ontologies. So now we're going to see a few examples from a few papers that were published in the last few years of how we can actually ingest this knowledge into BERT. So first of all, as we said before, there are two phases of training BERT, and we'll start with algorithms that inject knowledge in the pre-trained language model phase. So we'll start with UMLS BERT. So this is regular Joe. This is how the input to the regular BERT looks like. We have an embedding of position of the segment and the token embeddings. When we send it to med school with UMLS BERT, they add another layer of the semantic group of UMLS. UMLS, the highest layer, hierarchical layer of UMLS, contains about 50 different semantic groups, like disorder, like anatomy, like disease, and so on. And every term in UMLS is connected to one of the semantics groups. So what BERT gets here in the input is if he gets a word that is rare and he is not familiar with it, he already knows about it something from its semantic group in UMLS. He knows whether it's a disorder or an anatomy, and it gives him information about the rare terms that he might not have seen. Another change they did is that in regular BERT, in the pre-train phase, the BERT is trained to predict the mask word. In UMLS BERT, it's trained to predict the mask word or its synonyms in the ontology. So it basically learns the synonyms. And again, if the synonym is rare and not as frequently seen as the word itself, BERT would still know what it is. So UMLS BERT is very specific to UMLS, but there are also other algorithms that are prepared to be able to inject any kind of knowledge-based information into BERT. One of them is NoBERT. The reason that regular Joe here has the graduation cap is because NoBERT is basically a learning BERT. It's a BERT that can learn the specific embeddings of a certain knowledge base and inject them into the embeddings of BERT and get also the information from the knowledge base during the training of BERT. So in the paper itself, they trained it on Wiki and on WordNet, but we could basically replace it with UMLS and get a BERT that was injected with medical knowledge. And now let's talk about injecting medical knowledge in the fine-tuning stage. So what we saw before is actually opening BERT and rewiring it to be able to accept information from the knowledge graph. But there are also more elegant and more organic ways to inject knowledge into BERT during the fine-tuning stage. We said before that we have a lack of label data for fine-tuning in the medical world. Well, why don't we create synthetic label data using our structured knowledge? So this paper from a few months ago, they created synthetic medical task for BERT using the mesh ontology and using the structured nature of Wikipedia, which for a lot of disease uses the same paragraph titles and subtitles. So what they actually did is they took the concepts from mesh. They took the Wikipedia page of the disease, and they filled in the missing steps. So for example, here we can see what is the aspect of a disease. In the aspect, we put the subtitle. In the disease, we put the title. And the answer would be the paragraph after under the diagnosis subtitle. So we would actually get what is the diagnosis of COVID-19. Diagnosis comes from the subtitle. COVID-19 comes from the title and from mesh. And the answer comes from the paragraph under the word diagnosis. And in this way, they created a lot of question and answer paragraphs, and they fine-tuned BERT by predicting the questions and the answers. And then they showed that BERT didn't only get better in question answering tasks, but it also got better in tasks of medical language inference and name recognition of diseases. Basically, it's like the difference between dropping on someone the huge ontology of terms and explaining it with your own words and free text, which is a lot more suitable for the BERT algorithm. So what did we do today? We saw why medical records are hard. We saw how structured knowledge can help enrich our model with medical knowledge. And we saw that BERT can digest ontologies and get his medical degree. and probably beat me in how long before calling a real doctor again. Thank you very much.